Welcome to this video in which we are going to be discussing small signal modeling of differential amplifiers. So what we learn in this video is how to analyze differential amplifiers using small signal analysis, similar to what we've done for other circuits before. We'll then introduce the concept of what is known as a half circuit. Now half circuits provide a very intuitive and easy method to analyze symmetric circuits. Differential amplifiers that we've seen so far are symmetric circuits. So it gives us some understanding of how the circuit works. And then we'll discuss a few design examples as a part of the video. So now let's first begin with the differential amplifier. This is a standard differential amplifier that we've seen in our previous video. So remember that we're now talking about small signal gain, which means that all the signals shown here are small signals. So we have two input signals to this circuit, V in 1 and V in 2 applied to the gate of M1 and M2. Two output signals are created, VO1 and VO2, one at the drain of M1 and the other at the drain of M2. Typically we have a differential input, that is V in 1 minus V in 2, and we typically take a differential output, which is going to be the difference between VO1 and VO2. Now there are two modes of operation as we looked at in the previous video. One is known as the common mode of operation and one is known as the differential mode of operation. Right? So in a common mode, what happens is that you apply the same signal to both the gates and then you want to see what happens to the node that is at the drain. How does this output signal change because of the common signal that is applied to V in 1 and V in 2. This common mode signal is sometimes denoted when we're doing analysis as V in CM, CM indicating common mode. Now remember that when both the signals change, right, that is when the common mode signal is applied to these inputs, VO1 and VO2 are going to respond simultaneously, and assuming it's a perfectly symmetric circuit, both VO1 and VO2 are going to have the same gain to the respective gate terminals because the circuit is symmetric. So we define the small signal common mode gain as the relationship between the common mode input signal and one of the output terminals. Now please remember that this is an idealized circuit, and in the idealized circuit, if we take the output to be differential, that is if I define the output as VO1 minus VO2, then you're going to see that in common mode, both VO1 and VO2 are going to be the same, leading to the differential output being 0. Now we'll see that this is true only in the case when we have this ideal circuit where every component is matched and both these paths are essentially exactly identical. In reality, however, we'll see later that these paths are not necessarily matched, in which case even a circuit like this will exhibit a common mode gain even when a differential output is taken, but more on that later. Now let's talk about the differential mode. In the differential mode, you have a signal that is applied between the two gate terminals. So the differential signal is defined as V in 1 minus V in 2. And similarly, for the differential input signal, we define a differential output signal which is given by V out, and that is given as VO1 minus VO2. And therefore we talk about a differential small signal gain, and the differential small signal gain is essentially given by the differential output divided by the differential input. In other words, it's given by VO1 minus VO2 divided by V in 1 minus V in 2. Now let's first do initial ab initio simulations, and let's try and estimate the differential gain using the principle of superposition and knowing what we know about analyzing small signal in circuits. Right? So we'll do that and estimate the small signal differential gain. So the way we apply principle of superposition is we first zero one input, look at the impact of this input on the two terminals, then we zero this input and look at the impact of this signal on these two terminals. Again, to keep the analysis simple, I'm going to assume that M1 and M2 are perfect transistors with no channel modulation. So now when V in 2 is zeroed, that is when V in 2 goes to a small signal 0, Then if I see between V in 1 and VO1, then I see what is seen as a common source amplifier. The input is applied to the gate of M1, the output is connected from the drain of M1. So therefore you have a common source amplifier here. M2, however, provides a source degradation. Remember, in small signal, this current source is essentially going to be zeroed. So if you look at the circuit to analyze, you essentially have this common source circuit from V in 1 to VO1, and RD and M1. ISS essentially zeroed, and what you have is M2, which is the degradation transistor for M1, and then an RD connected to ground. And now we want to estimate V in 1 to VO1. Now, because lambda is 0 for both the transistors, what's going to happen is that RD is not going to be visible at the source of M2. So looking into the source of M2, you're just going to see a resistance of 1 by GM2. So this 1 by GM2 is the source degradation resistance, if you will, for this common source amplifier. So therefore I can write VO1 upon V in 1 as minus RD divided by RS plus 1 by GM. Remember, this is the resistance connected to the drain, this is the resistance connected to the source, and this is the input resistance of the transistor. And so if I simplify, what I get is my VO1 by V in 1 can be written as RD divided by 1 by GM1 plus 1 by GM2, because the source resistance in this circuit is 1 by GM1. Now let's do the second part of it, in which case we now want to see what is the gain from V in 1 to V02. Right? Now there again the circuit looks something similar to this. You have V in 1 applied to the gate of M1, but the output is being pulled from the drain of M2. So this is a cascade of amplifiers, if you will. So there is a source follower from V in 1 to this intermediate node Vx, and Vx to VO2 is a common gate amplifier. So as I mentioned, this to this is a source follower, and from Vx to VO2 is a common gate amplifier. And so I can talk the gain again, because the lambdas of both M1 and M2 are 0. Vx upon V in 1 is for an ideal source follower, so its gain is 1. Its R out, however, is 1 by GM1, looking into the source of M1. Similarly, if you look at the gain from Vx to VO2, Vx to VO2 again is a common gate amplifier. There is no source resistance, and so I have VO2 by Vx is equal to GM2 into RD. The Rn, however, is not infinity. It's a common gate amplifier, so the Rn is 1 by GM2. So I have two amplifiers connected in cascade, one which has a low R out, one which has a low Rn. So there is going to be some sort of a voltage division, and so therefore I can write my VO2 by V in 1 as GM2 RD into 1 by GM2, which is the input resistance of the common gate, divided by the input resistance of the common gate and the output resistance of the source follower, right? So this is the amount of the signal from the output of the first stage that falls at the input of the second stage. So therefore you get VO2 by V in 1 to be RD by 1 by GM2 plus 1 by GM1. Now normally when we design this circuit, we ensure that both these parts are symmetric. So we assume that M1 and M2 are identical to each other. That is, they have the same bias current, they have the same size. And so therefore in such a case, I can talk about GM1 equal to GM2 equal to 1 GM. Right? And so if I continue with this analysis, what I get is the VO1 to V in 1, that is the gain from V in 1 to VO1, is given by minus GMRD by 2, and the gain from V in 1 to VO2 is plus GMRD by 2. So note that the gain from V in 1 to VO1 is inverting in its characteristic, because VO1 is going to decrease as V in 1 increases. However, you see that VO2 increases as V in 1 increases. Now similarly, the second half of superposition is going to be when I zero V in 1 and apply V in 2. But we've already done this work, and we know that V in 1 and V in 2 are essentially the same signal because it's a symmetric circuit. So therefore what we'll do is, using the arguments of symmetry, we'll say that the gain from V in 2 to VO2 is going to be negative, and the gain from VN2 to VO1 is going to be positive using the same arguments. And so I have VO1 by VN2 as plus GMRD by 2 and VO2 by VN2 as minus GMRD by 2, right? And therefore the differential gain I can define as VO1 minus VO2 by VN1 minus VN2, which is GMRD, right? And that is expected because what's going to happen is when you apply a differential gain, you see that there is a difference in the drain voltages of the two transistors, which causes the differential output to appear, and that is given by GMRD. Now let's look at the circuit using the concept of half circuit. So again, let's revisit the circuit here now, and let's try and understand a different method of analyzing the circuit. So first thing you see in this circuit is there exists a line of symmetry. A line of symmetry around which the circuit is essentially identical on either side of this line of symmetry, right? And so what we can do is we can think about the operation of the circuit in two parts, one on either side of the line of symmetry. Now remember that we are applying a differential input between M1 and M2, right? So without a loss of generality, I can assume that a plus VID by 2 is applied to the gate of M1 and a minus VID by 2 is applied to the gate of M2, ensuring that the difference in the two gate voltages is VID or the input differential voltage. Now let's trace and see what happens to the currents in such a circuit. So I've applied a plus VID by 2 to M1 and a minus VID by 2 to M1. M1 is a transconducting component, M2 is a transconducting component. So what's going to happen is because of this positive VID by 2 that is applied to the gate of M1, M1 is going to pull a current of GM times VID by 2 from its drain to its source. However, because a negative voltage is applied to the gate of M2, a current GM-VID by 2 is going to flow upwards in M2. So what you see that in differential mode, you see the current flowing in M1 is downwards and the current flowing in M2 is upwards. So it's equal but in opposite direction. Now let's look at this output node A, right? So the gain from this gate of M1 to, so therefore what you see is that this GMVID by 2 is going to flow through RD, causing voltage at A to fall by GMRD into VID by 2. Similarly, this current is flowing into RD, so therefore VA prime is plus GMRD VID by 2. Again, what you see is that these two voltages are equal and opposite to each other. And so therefore, if I look at the gain from the gate of M1 to A, the gain from the gate of M1 to A is just minus GMRD. Similarly, the gain from the gate of M2 to A prime is again minus GMRD. So what you see is that these two circuits work exactly identical to each other, only difference being that the currents and voltages on either sides of the line of symmetry are equal and opposite. Now, an important concept you see is with this node P. Now, in the differential mode, what happens is if you think about this node P in small signal, ISS is zeroed, which means it's an open circuit. So technically P should be an open circuit node. However, if you look at P a bit closely, a current flows into node P, a small signal current, which is GMVID by 2, and the same current flows out of the node in small signal. So I have a node here where the same current is flowing in and flowing out of the node. So therefore, sometimes this node is known as the virtual ground, or it acts like a ground. It is not an explicit AC ground, it's not an explicit DC ground. But the way it behaves in a symmetric circuit is that it is able to source and sink the same current. So for all practical purposes, I can treat this node P as a ground signal, as a ground. And so hence we call this a virtual ground. So what you see here is that instead of analyzing this entire circuit together, all I could have done is just think about this circuit in terms of half of its circuit. So if I'm able to identify half of the circuit, then these are circuits which I've seen before. These are circuits which you know how to solve, right? And the gain of this half circuit, that is the gain from this gate to this output, is minus GMRD, which is the gain of this circuit or this differential amplifier in its differential mode. Right? So you see that this half circuit is able to give you all the information about the differential circuit. Now let's look quickly at the properties of half circuits. So again, I can think about these half circuits both in the common mode operation and the differential mode operation. Now in the common mode operation, the currents on both sides of the line of symmetry are going to be equal, right? Because both the inputs are moving in the same direction. However, in differential mode, because the inputs on either gate are moving in opposite direction, the currents are going to be equal but in opposite directions. Similarly, if I talk about the voltages about the line of symmetry, in a common mode operation, the voltages are going to be equal. In the differential mode, however, the voltages are going to be equal and opposite. And finally, because these two half circuits work similar to each other, in common mode, no current crosses the line of symmetry because no current is going to flow since the voltages across the line of symmetry are equal. However, what you see in this case is because the voltages are equal and opposite, at the line of symmetry, you're going to have a case where the voltage at the line of symmetry is going to be 0. So what you can do is using these concepts, given a differential amplifier, a symmetric differential amplifier, you can try and construct a half circuit and then use that to calculate the gain of the circuit. So let's look at a few examples. So here you're asked to find the common mode and the differential mode small signal gain of this circuit using the concept of half circuits. So again, this looks like a traditional differential amplifier. Only thing being that the current source, the tail current, has been replaced with this transistor M3, and I'll assume that M3 is in saturation. Now let's first identify where the line of symmetry of the circuit is. And you see that the line of symmetry passes right here through this transistor M3. So if I were to be very careful, I could actually do is replace this transistor with two transistors in parallel to each other, right? Whose effective width is going to be half that of the original, right? So that way when they're in parallel, I have two transistors. Now, in the differential mode, this transistor is not going to be of any use because P is going to become the virtual ground, which means that in differential mode, I only worry about what is above this virtual ground. So if I look at the differential mode half circuit, the differential mode half circuit consists of an RD, a transistor either M1 or M2. I've applied a VID by 2 to its input and I'm measuring the VO by 2 at its output. And this, if I assume lambda is equal to 0, the gain of the circuit is minus GMRD. So the differential gain of the circuit is going to be minus GMRD. Now let's look at the common mode gain of the circuit. So when you think about the common mode gain of the circuit and look at the half circuit, this M3, by design, this would present a resistance RO3, right, from this node to ground. Now, because I'm going to construct half a circuit, I'm going to construct this as two resistors, two RO3 and two RO3 connected in parallel. So if I think about my common mode half circuit, it consists of an RD, it consists of an input common mode voltage and output common mode voltage. Now in the common mode, this node is not the virtual ground because this node is not 0, right? Both these paths are going to conduct current. And so this M3 actually appears as a 2RO3 connected to the transistor. Again, this is something you know how to solve because this is a common source amplifier with source degradation. And so I can talk about the common mode gain as minus GMRD divided by 1 plus 2GM into RO3. So this is the common mode gain. And again, when I talk about common mode gain, I'm looking at the gain from this common gate terminal to one of the output terminals, right? And if I actually talk about the differential output, then obviously in this case, if I assume all components to be matched, the differential output is going to have a common mode gain of 0. Let's look at another circuit. Find the differential mode small signal gain of this circuit using half circuits, right? Again here, first thing to do in such problems is to first identify the line of symmetry. And the line of symmetry passes right here through this load resistance RL and through this common point and the tail current. So therefore, if I construct the half circuit consists of RD. Only half of RL is going to be part of this half circuit. So it's going to be RL by 2. Remember, these two nodes are going to be equal and opposite in voltage, which means that half of that RL by 2 is actually connected to signal ground, because right through the line of symmetry the voltage is 0. And if I look at this RS, again RS is connected between the source of M1 and the virtual ground, so that's also connected to ground. So for this circuit, the half circuit for this circuit reduces right there to the following circuit. Again, this is a common source amplifier with source degradation, and therefore I can write my differential gain as minus GM into the total load resistance, which is RD parallel RL by 2, divided by 1 plus GMRS, where RS is the source degradation resistance. Now let's look at another problem. Given mu P Cox is 0.25 mu N Cox equal to 100 microamp per volt squared, Vt is 0.4 volts and Va prime, now remember Va prime is the early voltage, is 15 volt per micron. That is the early voltage of a transistor whose gate length of 1 micron is 15 volts for a 0.25 micron technology. If the bias current, that is if the tail current is 200 microamps and all transistors have a channel length that is twice the minimum. So remember, this technology minimum gate length is 0.25. So what the problem is stating is that all gate lengths in this circuit have twice the 0.25 micron and are all operating with an overdrive voltage of 0.2. So both the PMOSs and the NMOSs are operating at a voltage of VOV of 0.2. You're asked to find the size of the transistors and the differential gain of the circuit. Right? So again, it's good to write down what all is known and then let's start solving the circuit. So given that all transistors have a channel length twice the minimum, the gate length of all the transistors is half a micron. Now branch current, because the tail current is 200, every branch is going to carry a current of 100 microns. So that's going to be the bias current for transistors M1, M2, M3 and M4. Now given that the gate length is half a micron, the early voltage for all the transistors is going to be given by 15 times half, which is 7.5 volts. So that's going to be the VA for the transistors. And so therefore I can talk about the RO for both M3 and M1, which is RON and ROP. Again, both are equal because the early voltage is equal and because the bias current in both these transistors are equal. So my RON and ROP, so both, remember, M1 and M2 are matched, M3 and M4 are matched. Therefore, the RO of M1 is going to be equal to the RO of M2. The RO of M3 is going to be equal to the RO of M4. And otherwise, I'm shorthanding this to say RO of the NMOS and RO of the PMOS. So the RO of the NMOS and the PMOS are equal, given by VA by ID, or 75 kilo ohms. Right? Now, all transistors need to support this 100 microamp of bias current. Why is it 100? Again, remember the tail current is 200 microamps with a VOV of 0.2 volts. That's given in the question. So because now I know the overdrive voltage of the transistor and I know the drain current of the transistor, I can calculate the size of the transistors needed, because in saturation, using square law, half mu N Cox W by L N into VOV squared is 100. Half mu P Cox into W by L P VOV squared is also 100, giving rise to the W by L's to be 16.66 for the NMOS and 4 times that, which is 66.66 for the PMOS. So we now estimated the size of the NMOS and the PMOS transistors. Now we need to find the small signal gain. Now the small signal gain, for that, if I construct the half circuit is just made up of this NMOS transistor and a PMOS load, and so therefore the gain is going to be given by minus GM1 into RON parallel ROP. So I need to first estimate the transconductance of the M1, M2 transistors. So the transconductance is given by 2ID by VOV. ID is 100 micron. So I have 2ID by VOV, or 1 millisiemens. So that's going to be the transconductance of M1 and the transconductance of M2. And therefore, the gain from half circuit is given by minus GM12 times RON parallel ROP, which is going to be 37.5 volt per volt. Remember, this is the convention. So you have positive, negative here. This is positive, hence it's minus 37.5. If I define VO to be the opposite direction, that is, if I define the plus here and the negative here, then my differential gain would be positive, right? So make sure that when you use these conventions, you accurately show which is the node which is considered to be positive, which is negative, and where is the potential difference being measured. Find the differential mode small signal gain of this using half circuits again. Again, here you have a 5 transistor circuit. So first thing first is start with the line of symmetry. So line of symmetry is right there. And so therefore when I draw the half circuit, my M3 is right there, my R is there. Now this point is going to be small signal ground. So that is shown here because it falls right on the line of symmetry. My M5 disappears because this node goes to virtual ground, and so I'm left with is this signal, this half circuit. Right? And again, this now is something you know because this looks like an NMOS transistor. This is a PMOS load. So I need to find the gain can be given by minus GM into the total load at the output. So if I'm standing at the output node, my R down is given by RO1. My R up is going to be given by RO3 from the drain of M3 and R from the drain to gate connection. And so from there I get the differential gain to be minus GMN into RO1 parallel RO3 parallel R. Right? So all the information about this circuit can be derived from doing this half circuit. Let's look at one last problem. Find the differential mode small signal gain again using half circuits here. So again here you see that you have 7 transistors here, but again the goal is to start looking at the line of symmetry. So the line of symmetry passes right there. Again in differential mode this node is going to go to virtual ground, which means you don't need to worry about M7. So all you're left with is this M1 transistor and then these two PMOS transistors M5 and M3. One is in saturation, one is a diode-connected transistor. Now again you know how to calculate the gain of this. So again R down is RO1. To calculate R up, I'm looking into the drain of M5 and also I'm looking into the diode-connected drain of M3. So total up resistance is RO5 parallel 1 by GM3 parallel RO3. So the total output resistance is going to be the parallel combination of the two, and therefore the differential gain is given by minus GMN into RO1 parallel RO3 parallel 1 by GM3 parallel RO5. So half circuits present a very quick method to analyze symmetric differential circuits. They're a very useful tool to understand how symmetric differential circuits work. Subsequently, what we look at is the impact of variation. So far we've looked at differential circuits which are identical, which are ideal. All transistors are matched, all resistors are matched. We'll see what happens when that's not the case, and almost all practical circuits have to deal with variations. So when you have variations in your design, you need to understand what happens to the output of the differential amplifier. And then we'll subsequently develop a single-ended differential amplifier. So one of the drawbacks of the current differential amplifier is the output is also differential. Many a times we'd like the output to be a single-ended. So we'll see how do you convert this now symmetric circuit to essentially an asymmetric circuit where the output is pulled from only one of the nodes.